Hello everyone, and welcome to today's chem lesson. Today we're going to wrap up our discussion on electrochemistry by looking at the two different types of electrochemical cells. The first type, the more common to understand type, is the Voltaic cell. And then a little bit trickier, a little bit less common, is the electrolytic cell. Both types of cells use electrodes, and they're two pieces of metal, they're solid pieces of metal that allow for the changing of a pure element into an ion or an ion into a pure element. The two electrodes each have their own specific name. The anode is the electrode where oxidation happens. The cathode is the electrode where reduction happens. And we've got a little mnemonic we can use here to remember that, right? Anox, anode, oxidation, red cat, reduction, cathode. For voltaic cells, they will be spontaneous if table J agrees with the way the reaction is written. Or, alternatively, you have to draw them, you have to make them, you have to write them in a way that agrees with table J. Now, table J is not a new table. Table J is an old table. Table J is the activity series. If you remember, the activity series was the one we used when we looked at the single replacement reactions and whether or not they would be spontaneous or not. And the way we talked about that, what we said the higher element on the table gets to be in the compound. And that's not a great description, that wasn't a great definition, but we couldn't really talk about the actual reason for table J, the actual reason behind table J, because we did not have the vocab words oxidation and reduction. But now we know what it means to be oxidized, and we know what it means to be reduced. And so we can say that metals in the metal column that are high up on the table are good at being oxidized. Right? Good at oxidation. Metals that are low on the table are bad at oxidation. Right? These metals at the top are really good at losing electrons. These metals at the bottom are bad at losing electrons. For the non-metals, it's being good at reduction, or, in the case of iodine, bad at reduction. And this is all relative. This is relative to each other, right? Iodine is really good at being reduced, but just not as good as bromine, chlorine, or fluorine. Right? Something like zinc is pretty good at being oxidized, but just not compared to these elements above it. And so when we look at a reaction, we look at a redox reaction, let's say this redox reaction, if we're looking at this redox reaction and we're trying to figure out if this agrees with table J, what we want to look at are the two elements. Zinc is being oxidized. It is losing 2 electrons. Copper is being reduced. It is gaining 2 electrons. So the question I need to ask myself to find out if this is spontaneous or not is zinc higher on the table than copper? And in this case, it's true, right? Zinc is higher. Zinc should be oxidized. Copper is lower. Copper should be reduced. Because zinc is better at being oxidized. Now, how do we take a redox reaction like this one and turn it into something that produces electricity for us? How do we turn this into a battery? And that's where we're going to get a new type of diagram. Here, we have the diagram for a voltaic cell. We're still looking at the same combination. We're still looking at the zinc and the copper. Right here, we're going to put the zinc ion. Here's my zinc metal, my copper metal, my copper ion. If we keep the zinc and the copper separated from each other and use a wire to connect them, the electrons that are lost by the zinc can travel up through the wire over to the copper. Anytime electrons pass through a wire, that's electricity. So anytime they pass through this wire, we are generating electricity. Everything we know about this copper and zinc reaction is still true. Everything we talked about in our previous lesson is still true. And we're going to go into a little bit more detail in a second. The salt bridge helps to balance out the charge, helps to balance out the flow of charge from one side to the other. When electrons move from left to right in this reaction, negative ions flow from right to left. And that combination, that flow, that counterflow, allows for the circuit to be completed. Electrons are always going to flow from the anode to the cathode, from the thing that gets oxidized to the thing that gets reduced, just like we looked at in our previous lessons. The anode is going to be negative for a voltaic cell because the anode is the source of electrons. It is producing electrons. Electrons are going to be hanging out on this piece of metal, and that's going to make it negative. The cathode is going to be positive because once the electrons get onto the cathode, they're going to get merged, right? The copper ion is going to get reduced by those electrons, and so they're going to get immediately used up. Let's take a look at this cell in a little bit more detail. Right? Let's clear it out. Let's look at this reaction. This is the same reaction that we looked at a minute ago. We know that the zinc is going to be oxidized, the copper is going to be reduced, and we know that that agrees with table J. All right, let's take some bullet point notes here. Zn0 is oxidized. It loses electrons. Copper plus 2 is reduced. It gains electrons. Electrons are going to go from, right, they travel from the zinc metal to the copper ions. The other thing we know is that zinc is higher than copper on table J. These are things that we knew before this lesson. Let's put some new stuff in, right, some new labels in red. The thing that gets oxidized is always the anode. The thing that gets reduced is always the cathode. For a voltaic cell, the anode is negative. The cathode is positive. The electrons are going to travel from zinc to copper. The electrons are going to travel from anode to cathode. We're going to go from anode to cathode. let's put in our labels again from before. Here's our copper ions, zinc ions. Every time this zinc gets oxidized, it's going to create 2 electrons and a zinc ion. The production of electrons is what makes the anode negative. But zinc doesn't want these electrons. These electrons are being shedded. They're being gotten rid of. And zinc 0 doesn't have a negative oxidation state it can become. So these electrons are going to travel up through the wire, passing whatever thing you're trying to power up. In this case, it's a light bulb. And go down into the copper electrode. The negative electrons here are going to attract the copper ion, and together they will become copper 0. The copper ion will be reduced. And this is going to happen over and over and over and over and over again until we run out of one of our pieces, until we run out of zinc, until we run out of copper, until the salt in the salt bridge runs out. Any one of those things. I do have an animation here, so let's take a look at this animation. Here we've got that same setup. Here's our zinc, our copper ions, all the same. We know that the zinc is the anode. It's going to get oxidized. We know it's going to be negative. We know the copper is the cathode. The copper will get reduced. The copper will be positive. We know that the electricity is going to flow. The electrons are going to flow from anode to the cathode. And we know that the salt bridge is here to balance out the charge. This is where we're really going to focus in on the salt bridge. So let's watch step by step, atom by atom. First, the zinc gets oxidized. A zinc atom becomes a zinc ion and makes 2 electrons. Let's look at the total charge in this cell. Before the zinc gets oxidized, right, going backwards, we have all zeros. So the total charge in here is 0. Then the zinc gets oxidized. Now we have a zinc plus 2 and 2 electrons, still 0, and a bunch of zeros. So the total charge here is still 0. But then, like we said, zinc doesn't want these electrons. These electrons are going to go all the way across to the copper. Before we focus in on the cell with the copper, let's stick to our anode here. The total charge in this cell now, in this beaker, is not 0 anymore. The total charge in here is a positive 2. Because we had 2 electrons, 2 negatives, that then left. This is where the salt bridge comes in. The salt bridge is going to send in 2 negative ions to cancel out the charge that was lost when those electrons left, bringing our charge back to 0. On the cathode side, we're going to have the reduction of a positive 2 ion. We're going to lose 2 positive charge. And so the salt bridge is going to come in and give us 2 positives to replace the positive 2 that we just lost. And then it's going to happen again. Zinc gets oxidized. Electrons move to the other side. Negatives move to balance out the electrons from the other on the anode side. The copper ion gets reduced, positives move in from the salt bridge to cancel out the positive charge that we just lost. And then it happens again. Zinc gets oxidized. Electrons move across. Salt bridge balances the charge. Copper gets reduced. Salt bridge balances the charge. And then it happens again. Over and over and over and over and over again. Now this is going to keep happening until we run out of one of our pieces. And in this case, we actually run out of 3 pieces at the same time. We are now out of positive ions in the salt bridge, negative ions in the salt bridge, and copper +2. Even though we still have zinc left over, if this zinc gets oxidized and makes 2 electrons, those electrons have nowhere to go. If they move through to the other side and they hang out over here and we get 2 more electrons, there's nothing left that's going to take electrons. There's nothing left to be reduced. So this battery is now dead. Finished. Take it out of your Xbox controller and put in a new one. Let's do a little bit of practice. Here we have very basic models of 2 different Voltaic cells. Right? One over here and one over here. I want you to take a look and see if you can fill in each of these labels. Which one's the anode? Which one's the cathode? Which one is oxidized? Which one is reduced? What is the half reaction for each of them? Where are the electrons going? And what is the full balanced reaction? In order for you to do this, you must use Table J. Table J is going to tell you which one is the anode and which one is the cathode. But you have to look at it in order to know. Pause the video here and get started. Okay, so let's look at some answers here. When everything gets filled in, we get answers that look like this. First things first, the anode is higher on Table J. So when you look, you compare barium to iron. Barium is higher on Table J. Barium is the anode. Anode is oxidized. Iron must then be the cathode. Cathode is reduced. Electrons flow from anode to cathode. And your half reactions should be taking the ions and the atoms from the cells. Finally, at the bottom here, forgive me, I ran out of space, you get your final balanced full reaction. Remember, for a balanced reaction, the number of electrons lost must be equal to the number of electrons gained. Since the iron here is gaining 3 electrons, I needed 3 copies of barium to each be oxidized. So 3 bariums become 3 barium plus 1s, right? 3, 3, 3 to make these numbers equal. And that's how I balanced it out. I did the same thing in the second cell. Tin is higher than silver, so tin is the anode. Tin is oxidized. Silver is the cathode. Silver is reduced. Electrons flow from anode to cathode. I wrote my half reactions based on what I was given in the cells. And then I made sure to make my electrons equal. Right, multiplying this side by 4 to write my full balanced half reaction, or full reaction. I have another set for you. Same idea, give these ones a shot. Pause the video and unpause when you're ready for some answers. Our answers here are going to follow the exact same logic that they did before. The thing that is higher up on table J is the anode. The anode gets reduced. The other thing is the cathode. Wait, I said the anode is reduced. That was foolish of me. The thing that's higher up on table J is the anode. The anode gets oxidized. The other thing is the cathode. The cathode gets reduced. Electrons flow from the anode to the cathode. Your half reactions are written based on what is given to you in each cell. You know your start and your finish. Your balanced full reaction makes sure that the electrons gained and lost are equal. So you need to multiply one or both reactions in order to make those numbers equal, or sometimes, like this last one, you just leave them alone. And those are Voltaic cells. But earlier in this video, I said that there were two different kinds of cells. The second kind of cell is an electrolytic cell. This kind of cell, an electrolytic cell, opposes table J. It is non-spontaneous. We use a battery or some sort of power source to force a reaction to happen, to make a non-spontaneous reaction happen. Instead of creating electricity and generating electricity, electrolytic cells take electricity and make it into chemical potential energy. In an electrolytic cell, the anode and the cathode have reversed charges. The anode is positive and the cathode is negative. We'll talk about that in a second. Electrolytic cells are most commonly used for stuff like this in this picture, forcing the oxidation of silver and then forcing the reduction of silver onto another thing. This diagram shows the silver plating of an iron spoon. Right, we force the silver to become silver plus 1, and then we force the silver plus 1 to become silver 0 again. On the spoon, on the thing we want to give a light coating of silver to. Now let's take a look, right? Let's jump back for a second. We said this one was a Voltaic cell. Right? We said that zinc is oxidized. We said that it was losing electrons. We said that it was the anode. We said that it was negative. We said that copper is reduced. We said that it's gaining electrons. We said that it's the cathode. And we said that it's positive. We said that electrons travel from the zinc to the copper, from the anode to the cathode. We also said that zinc is higher than copper on table J. That was our Voltaic cell. This is the kind that gives us electricity. But when we looked through our animation, the battery died. Right? We ran out of copper ions. We ran out of ions in the salt bridge. We couldn't continue to oxidize the zinc. But does every battery permanently die when it's done? No, absolutely not, right? You've got phone batteries that are rechargeable. You've got laptop batteries, iPad batteries, right? All sorts of devices that have these rechargeable batteries. But that only happens when you plug it into the wall, when you plug in that thing to a power source to force it to recharge. When we look at an electrolytic cell, we're going to look at just recharging this cell specifically, the equation is going to flip. The zinc 0 is going to be a zinc plus 2 now. The copper plus 2 is now the copper 0. We are forcing the exact opposite of this previous reaction to happen. In this case, the zinc is being reduced. It's gaining electrons. It is the cathode. The copper is oxidized. It's losing electrons. It is the anode. Right? By flipping the equation around, we have swapped the anode and the cathode's positions. Right? Now the anode is the copper and the cathode is the zinc. Now the electrons are still going to travel from anode to cathode. From the copper to the zinc. From the anode to the cathode. The zinc is higher on table J. Higher than copper on table J. Electrolytic cells do the opposite of what table J tells them. Right? They force the opposite reaction to happen. Now the new part, the trickiest part, is that in an electrolytic cell, the charges are the opposite. The cathode is negative, the anode is positive. Why does that happen? That happens because we have to force this reaction to occur. The battery, the power source, pushes electrons in to the cathode, forcing all these electrons to hang out on the cathode. That makes the cathode negative. You're pumping in all these electrons. On the other side, the other end of the battery pulls the electrons out of the copper, tears them out of the copper, and forces the copper to get oxidized. And because we are ripping out these electrons, forcing this oxidation, the anode, in this case, the thing that gets oxidized, is positive. It's a change of what normally happens. It's the opposite of what normally happens. But the nice part about this is that it allows us to reset the battery. To reset the original battery, this battery. And then we can go back, and when you take this battery out and replace it with a light bulb, the reaction flips and you go back to being a voltaic cell. The zinc gets oxidized again. It loses electrons. It is the anode. The copper gets reduced again. It gains electrons. It's the cathode. And the reaction runs over and over and over again until it runs out of energy. Then you take out your light bulb and you put in your battery, and the reaction flips again. And it becomes electrolytic. The battery forces the reduction of the zinc. Pumps in those electrons, pushes in these electrons, forces the zinc ions to be reduced. And it resets the battery. And this process, this back and forth, this alternation between Voltaic and electrolytic is what allows us to do things like have rechargeable batteries, have phone batteries that you don't need to replace every time it dies. Right? These are the modern marvels of modern batteries. It also happens to be the end of the lesson and the end of the unit. So with that, I'm going to wish you all a wonderful day.